I'm based in Kyoto at the moment. I'm a researcher at Kyoto University. I'm from the UK. I did my PhD at the University of Bristol, and I'm actually moving back to Bristol to begin as a lecturer there from February. So the work I'm going to talk about today is kind of split across those two things, and they kind of overlap a little bit as well. And then also because both Kyoto and Bristol have a very nice community of people doing what I kind of think, what you guys are doing here, where you've got this very sort of like dynamic co-working space where people, I guess, from a lot of different backgrounds and kind of daytime lives, like come and work together on all of these different things. So I wanted to talk a little bit about that as well. But the main thing that I'm going to focus on is the aspects of my research that looks at energy autonomous artificial organisms. So in Kyoto, I have like a small group of people, and we look at a number of different things. So in general, we're sort of looking at soft and bio-integrative robotics. So this covers things like energy autonomy, soft robotics, or things like locomotion and sort of sensing. Wearable technology, a little bit of sort of predictive behaviour through simulation, and now we're sort of looking into a bit of work on agricultural robotics.
What are we looking at?
Oh, sorry. So here we've got sort of soft actuators at the top, which I'll talk a little bit more about today. The sort of sketch and 3D model on the left are an agricultural robot that one of my students is working on. We've got Mirror Hatband, which is a sort of haptics combined with neuroscience projects that we're doing with the University of Hydrogel. And then at the bottom, we've got some bacterial fuel cells that I'll talk a bit more about, and some field testing that we've been doing to look at sort of how we can use the things that we're working on in the lab in the field in a way that allows them to be energy autonomous. So in all of that, we're kind of trying to look at a couple of things that I sort of feel like nature does really well amongst a lot of things. So one of these things is having soft bodies with robust adaptability to different kind of situations and environments. And another thing is having energy autonomy, so the ability to sustain an organism's own energy needs just by the life that it needs. And quite often this is through interaction with other living things, right? So these are kind of built around different relationships, things like photosynthesis, homeostasis, so how we regulate our own kind of internal balance, symbiosis, where organisms sort of build relationships with each other, chemotaxis, so the way that we kind of find food, and ecosystems themselves, so these big interactions of different organisms within complete systems. So in this work, we've sort of looked at combining bio-inspired actuators with a bio-inspired energy source to try and create robots that encompass some of these things. So in taking the idea of a robot, we've sort of looked at three main aspects. One of these being the sort of muscles and how a softer body of a robot can allow it to be more sort of robust in some ways. And then how a robot can have a stomach or a metabolism, so how it can be energy autonomous in a way that's very close to how living things are. And the third thing is then just how these two things are kind of combined through the behaviour of the organism, and so in that we kind of term these things artificial organisms rather than robots. So we start with the sort of stomach of the robot, and how we've been building these is by using microbial fuel cells. The microbial fuel cell has two electrodes, and so it works in the sort of the same way that kind of like a battery does. We have one electrochemical potential generated at one electrode and a sort of opposing charge generated on the other side, and so from that we can harvest electrical power. So on the anode side, here we have sort of biological substrates that come into this side, and they interact with a community of bacteria, and those bacteria can come from anything from like pond water to sediment to soil, so they're very kind of ubiquitous and easy to introduce to the system. And through that bacteria's respiration, electrons are released the same way that they are when we respire. And then on the sort of opposite side of this cell, we have a flow of protons across this proton gradient through the cell. To balance that, the electrons that are released by bacteria create electrical current through some load, and from that we can harvest a small amount of charge. So we were working with these for a number of different reasons, partly because, as I mentioned, we can find these bacteria in a lot of different sort of natural, easy to access environments. And what that means is we can build systems that, in theory, we can introduce back into the native system that they came from without causing any disruption, because the organisms that are used to run the system have come from where, like this robot that's going to have the input is going to operate. We're then starting to try and use biodegradable materials to actually build these systems. So in the image that I had on the last slide, we've got this central part in between the two electrodes, which is a proton exchange membrane. Previously we were buying these from companies that made chemical fuel cells, but we've started making these out of natural polymers, very much like you're doing, with things like natural rubber latex, so something that will be ionically conductive, but will kind of break down as well. And we've noticed things like, whereas the synthetic material degrades with time and gets worse, the natural material actually increases its performance over time, and then eventually the bacteria can just eat all of it, and then there's nothing left at all. So it kind of has this life cycle where it grows, it develops, it gets better, and then it destroys and consumes itself. So these types of fuel cells, they've been used sort of for electrical power in a number of studies, but they were sort of mainly focused on as biosensors initially, and this is where we're kind of starting to direct our focus as well. So the biofilm, the bacteria living inside of these cells, they're really sensitive to things like pH change, temperature, the energy content of the stuff that they're eating. And so what that means is, because they're releasing energy at sort of in some proportionality to that, we can use that as a biosensor by detecting and analysing the voltage that they give out. They're also kind of breaking down the material at the same time, so they're contributing to the biodegradation of anything that comes into the cell. So how we kind of see this working is something where you have something that's providing power, it's providing sensing, but it's also providing a part of a kind of ecosystem where it's breaking stuff down. So this could be things like algae, sort of large blooms of algae, and because these sort of bacteria could also break down things like petrochemicals, we think these could potentially be used in things like oil spill cleanup. So, coming back to this idea of an artificial organism, we wanted to use these primarily initially as the power source for the robot. And this had kind of been done before at Bristol. So there were these wheeled robots that you can see that had these very large kind of banks of a very large number of microbial fuel cells, so the cells on board. There's a sort of natural limit to the amount of voltage that one of these cells can produce, because they're based on these kind of coupled natural reactions. So each cell can produce sort of around 700 millivolts maximum when it's kind of a workable power output. So that's not very much, right? So we kind of couple them together in series to produce a higher voltage output. But this leads to problems because of the sort of wet engineering of these systems. You've got fluid passing through, it's typically containing a lot of particulate matter, and so things get stuck, things break down. And this sort of energy autonomy that we're trying to work towards very quickly kind of comes to a stop. So we wanted to look at what would happen if we took one bacterial fuel cell and to see if we could design a system that could be self-sustaining, but just using one artificial stomach. So we built this robot because it rose along. And the idea with this was to focus on something that was smaller, something that was softer, and was therefore kind of closer to something that could potentially operate in the real world. But could it kind of operate on its own? Could it sustain its own sort of life cycle? And while this is kind of built of a lot of kind of metal and plastic components, we wanted to sort of explore this idea and whether we could introduce some of the stuff we would do with biodegradable materials to build the system. So we started with the stomach again, and this kind of looks very like cumbersome and box-like because we were comparing it to the sort of equivalent lab, like bench lab experiment. So in trying to see if something could give us like comparable performance to that, we wanted to use something that was very kind of structurally similar. So it's not really that beautiful or organic looking at all, but it does kind of function as a battery. So we started with, okay, we've got to have this single fuel cell. We've got a very well characterized MFC design. This is used a lot in kind of like research experiments looking at changing other parameters. We wanted to have a swimming robot where our fuel or our food for the stomach is now not kind of someone like feeding the robot or the wheeled robot moving to like a dispenser, but it's kind of now in the robot's immediate surroundings. So we started thinking about how to feed it and whether we should use like a pump and have something kind of continuously flowing through the robot to sort of syringe feed it like we were doing in the lab, or whether some kind of diffusion into the cell would work. And in the end we decided to give it a mouth because it's kind of how we feed, so like it sort of made sense that the robot would do it too. So in that we sort of started working on this cycle. We've got the fuel cell, we've got the stomach that needs to kind of eat food, and we've got this sort of basic behavioural cycle where the robot's going to charge up. All of these, the previous sort of images that I showed of robots before, none of these work continuously. They work with sort of pulsed operation where they're storing up enough energy to run things like electromechanical actuators in order to generate this motion. So the robot's going to store up energy, and then it's going to open its mouth, eat some food, and then produce some like sort of work output on top of that. So some kind of net sort of output in order to sustain itself. So it's got mouths to eat, it's got paddles to swim. The idea of the feeding was based on a couple of natural behaviours. One of these being sort of ram feeding, where organisms like the basking shark and manta ray have very large kind of mouths and swim through fluid in order to kind of take in food. And the other thing is suction feeding, where some bony fish will open their jaw very wide in order to create a cavity and use that to sort of draw in fluid. So in that we create this very kind of large opening and closing sort of folding structure in order to displace the food that was inside the fuel cell, which is typically kind of particulate, muddy stuff that belongs at the bottom of a pond kind of thing, and fill it with fresh stuff. The other thing that we wanted to consider with this is that, okay, we've got one stomach and we're trying to prove this idea that we can have something that's energy autonomous, but like without being the stack of fuel cells. But it might be that in certain circumstances further along the line, if this works, we want to have robots that are able to join together. So we thought about the behavior of the amoeba, where these exist perfectly happily as individuals for all of their lives, unless there's some kind of stress in their environment. So unless it's a stressful situation like lack of food or some kind of toxic, presence of something toxic. And in that situation, they're all using sort of decentralized communication or core sensing, or however they want to do it, like group together, form this kind of like Mexican hat shape, form a fruiting body, and then shoot their spores out to the to sort of propagate the swarm somewhere else. So our sort of thinking with this was like, okay, well, we have to have something that in water could allow our robot further along the line to maybe do something like this, to join together if it needed to, even though it could behave self-sustainably by itself. So the problem with this is that we've got this 2-electrode system. We've got one of them in contact with the water when the robot's feeding, and so all of these are then connected together. So if we think of these as our little fuel cells, all of them are sort of grounded together, which means we can only have them arranged in parallel, which means we limit the voltage output from them, and as we've hopefully got from up until the point, that's the kind of limiting factor. We want to multiply the voltage output from them, and we can do that through sort of amplification circuitry. We wanted to have something where they could just be linked together. So this partly determined why we had this kind of folding structure for the mouse, so that we had something that didn't need kind of valves or complex sort of opening closing systems to isolate it completely from the surrounding fluid. Because these are kind of really low voltage systems, if you have any sort of trace couple in between one system and another, it's going to affect the performance of it. It's not sort of like having a little bit of water around an electrode that is, otherwise kind of fairly immune to that. So in that we could join them in series and hopefully have higher output robot later on. With our propulsion design, we now have this huge mouth on our robot, and we kind of have to think about how it's going to move along. So we looked at the water boat in beta and how it kind of swims along the surface of the water, and developed a sort of rowing mechanism for the robot to row along. So it's kind of not the most efficient mode of transport, but in this, we sort of just wanted to show that it could do something, locomotion, in addition to this sort of energy autonomous behavior where it feeds. So we can see the robot move in this video, the electronics are all off board because they just haven't been waterproofed enough yet to be on board. But they weigh about sort of 25 grams. So
real speed?
So this is real speed, yes. Yeah. So the robot opens up. It's also in clean water here, so you can see its motion because in dirty water you can't really see underwater. It moves along a little bit. This was sort of about the daily distance that the previous larger robots would also move. So looking at kind of comparable like locomotion to the others, even though I'm not really influencing that. But this, what we could show with this was that the whole system could produce more energy than it would use up in order to feed itself. We showed that it didn't need to move it didn't need to move along in order to actually displace the fluid inside of it, and so so the feeding part is energy autonomous, and everything it does on top of that is kind of net gain. In this case, being a small amount of locomotion, but this could be used for other things. So we've got these three different parts. The robot has some sensing. It has kind of internal sensing or proprioception in the sense that it senses the sort of position of its, like it senses if its mouth is open or closed. So if it gets stuck, it knows about it, and it knows to try and repeat the opening or closing until it's sort of an end condition is reached. And it's also doing, to some degree, this sort of homeostasis where it's waiting until it's got enough energy to do something and then it's kind of empowering itself. But it's not really doing any sensing of the world. It's not really kind of like responding to its environment in a closed way. It's not doing external sensing to find food, and it's not doing this to monitor the presence of a substance, which are the two things that we sort of thought this could be used for, either a kind of chemotactic type behaviour or something to be used maybe in environmental monitoring. So, so I said this current behaviour is sort of controlled by this homeostasis. But what we wanted to do is to try and look at how we could develop this to allow the robot to feed on natural substrates and pollutants, so things like algae, petrochemicals and wastewater, in order to see if we could use this sort of thing in things like environmental remediation, remote sensing and monitoring. So we started focusing back on the sort of biosensing that these cells, microbial fuel cells can be used for. Because the one thing that we can power at least near continuously with this computation, or at least near continuously with one is computation. So we can run, for example, a very sort of low power microcontroller that while it's asleep will consume sort of microwatts, and when it's awake will sort of consume in the order of milliwatts. So the nice thing about these sensors is that they are energy autonomous. You also have something where you can sort of maybe wake up when needed and be sort of dormant or asleep when not needed. The disturbances, or the things that this is maybe going to detect, directly affects the oxidation of fuel, which affects the anode potential, and the reduction of an oxygen, which affects the cathode potential. So you can then, in theory, specifically monitor a parameter by monitoring changes in pH or COD, BOD, so the chemical or biological oxygen demand for that particular sample, the presence of a toxicant, and the presence of biological components. But this signal, this output is affected by a lot of different factors. So it's like you can sort of picture that you might train a pH, but in a lab you might want to keep everything, you need to keep everything else constrained in order to identify that it was pH that changed. So what we're doing now with these systems is to use them as sort of self-powered analysis machines, I guess, for trying to identify parameters about water samples, given things that will change in relation to a lot of different parameters. So we take a water sample, we put it into a microbial fuel cell. The energy from that is then harvested the same way as it was before. But in this case, the electrical power is now being used to power a microcontroller that's running an embedded machine learning algorithm, and that machine learning algorithm is analysing the same signal from the cell. And so in doing that, we can now, we're using this at the moment to identify COD, so to identify the chemical oxygen demand of the water sample. We've started with this because it seems to be like a common parameter that's used in water quality analysis. It's also something that at the moment seems to be predominantly lab-based. You can do this in line, and you can do it like sort of as a distributed sensor, but it's very expensive. And it's kind of relatively high power. It's not something that's really been sort of deployed as like a sort of IoT type device yet. So we thought, okay, we can do this with with these systems, then maybe we can expand this and look for kind of other types of analysis that we can do. So that's the project that we're working on at the moment, and then we're trying to then sort of integrate this into other types of systems. So we're showing this as we're sort of now in the process of demonstrating this as a closed loop operating system from, we think, from 2 of the MFCs that I showed you at the moment, and hopefully soon with just one MFC. And we're now sort of exploring this idea as energy autonomous distributed sensor networks by partnering with Homeostasis City Farm, who are a farm in Kyushu in Japan, who want to look at sort of the relationship between fish and plants on their aquaponic farms in order to make the system completely autonomous. So this is kind of, I guess, like quite a new, it's not really a new farming technique, but it's kind of new in terms of something that's being sort of scaled to being industry deployable. So in this, I guess some of the main concerns that we sort of seem to hear from this company are that they haven't really identified strongly relationships between the sort of overall population of plants and the overall population of fish. So what they want to do is to try and use distributed sensing to try and understand a bit more about how they can keep balance in the system but across a larger scale. And so in doing that, we're going to try and use this to sense. This is also an undergraduate project that's going on in our lab. I think this looks a little bit like a missile at the moment. But the idea with this is to create a modular deployable robot, so something that could be used as a mobile lab. So if we have a robot that we want to kind of deploy and use for sort of sensing or analysis in the fields, I think this sort of very quickly turns out to be like a very large robot. You try and put a lot of different things on board in order to do the full suite of testing that you maybe want to do. So the idea of this is to create something that is modular so that we can kind of swap in different testing arrangements in order to have something that's small enough to kind of move around, something like the aquaponic farm or a sort of aquaculture setup, for example, but still be able to kind of deploy the different tests that people want to put out into the field. So in this sort of biosensing work, ongoing things that we're doing are stuff like miniaturization. So at the moment we work with these quite large fuel cells. They're about 25 millilitres in terms of the fluid sample that they hold. And that's enough power to power our systems of energy autonomously, but it's kind of a long period of time to wait for a test result, particularly when we're sort of thinking, okay, well, how long does it take for a lab test to come back? But smaller cells give a much faster sort of electrical output because they're consuming the material that's inside them much faster. So we're now looking at having like single sensors and sensor arrays made out of exactly the same types of fuel cells, just smaller, and then having another cell using the same type of system but larger to sort of be the power component of the setup. Because we've shown quite nice results so far with the analysis of one parameter, we're now just sort of trying to expand that out to other things that we could try and identify and sample with. So things like dissolved oxygen, because we know that the MFC responds to the amount of oxygen around because it needs an oxygen to sort of to function. So this is our sort of next step in what we want to try and analyse. If we can then have this faster sort of analysis of the signal, this sort of leads the way to having something that's maybe able to demonstrate chemotaxis. So at the moment, if we're sampling once a week, moving in the direction of sample, things in the environment could probably change like within a week. But if we're doing that over the course of a day, maybe it becomes something more feasible for chemotaxis. And this is also linking with some of the work that we're doing on sort of simulating distributed groups of organisms. And some of the behaviours that I mentioned at the start, where life kind of uses interaction with other types of life to support its own self-sustainability. So using prophylaxis, so using kind of agent-to-agent feeding, because we're dealing with things that actually kind of ingest physical food in groups of robots. And then how this sort of looks from an environmental remediation point of view, because they're only really taking this small amount of fluid. So we wanted to look at okay, how big a kind of impact can this actually make in terms of breaking down contaminants in the environment. We also have a project about the lazy worker phenomenon, which is a sort of phenomenon observed in communities of ants, where only something like 10% of the ant population are kind of super active all the time. So the rest of the population are just chilling out the rest of the time. And this varies, you know, so you've always got sort of about 10% active. They're not the same people, they're not the same ants all the time. But this has been sort of observed in these natural colonies to have a kind of more overall energy efficient output of the system than having everybody work all the time as much as they possibly can. So it's quite a kind of low percentage, and we're now looking at kind of simulating that and how this could be sort of paired with these types of energy autonomous robots. Is a robot being attacked? Okay, so the other parts of our artificial organism that we kind of focus on are things like the muscles, and we've got a number of different projects in the lab that look at soft actuators and artificial muscles. So a lot of the benefits to using and working with robots that are soft are things like multi-degree of freedom, in a lot of cases infinite degree of freedom, actuation, toughness, compliance, so being able to kind of adapt to different sort of object shapes or environment shapes. Biointegration, so things that can be used in the body, the sort of safety that comes along with that, and then having things that are with low noise actuators as well. So one part of that we're looking at are hydrogel actuators. So these are a class of super-absorbent polymers. They absorb water in order to actuate, so they need to be in a kind of aquatic environment, which for swimming robots kind of thing. They produce really large strains and sort of workable force output given the sort of size of them, and they're stimuli responsive, so they'll respond to things like changes in temperature, changes in pH, some of them electrical stimuli. And they actuate by going through this sort of phase transition. So they start off, so in their sort of soluble state, they are hydrophilic, they form these kind of long chains, and they're very kind of solution-like in terms of the material quality. And when you apply this kind of external stimuli to them, so for example temperature above a certain critical temperature, they become hydrophobic. The molecules essentially want to stick to each other, stick to themselves more than they do to the water around them, and they form these globules. So you expel the water, this polymer aggregates, and they become kind of a small compacted rubbery substance. So we're kind of interested in these. We look at a lot of different types of soft actuation in the lab, and we have projects that look more at kind of the sort of electrostatic magnetic actuators for things like locomotion, because they're kind of faster and like the response is a lot faster. Hydrogel actuators are typically pretty slow. They've got to rely on diffusion in order to expel water from them. But we're sort of interested in them from the perspective of their capabilities to be similar to natural muscle in terms of how they, like the force and strain that they can output. And also that they exhibit these transitions around the really kind of workable environmental temperatures. So they sort of show the potential to be energy autonomous in like real sort of weather systems, I guess, or like real observable kind of environmental temperature changes that we see. So we've been working with two sort of categories of gels. So the first of these is sodium polyacrylate, and it's a gel that will just passively absorb water. So you might have seen it because it's like sold as a toy and also for plants. So people sometimes grow plants in and they look like these sort of bubbly jelly things. So they store water. They sometimes sort of in the ground they store water and they'll release it at a slower rate. And they produce really large strains, but the problem is they do this passively, so you can't really sort of reverse it. So we use these as a sort of simulator gel, if you like, to kind of see what we can do with something that will expand like this, but whilst sort of learning how to synthesize these things. So while doing that, what we've been working on is sort of making gels that will actuate in response to temperature. And we're doing this as a collaboration with polymer chemistry at Kyoto University, and making gels that will actuate at temperatures that we kind of observe in real life. So sort of one of them that we work with has a transition temperature of 32 degrees, and another one is sort of 17 degrees. So we can picture how we might use these, or how we could have things that would actuate in response to sort of daily night and day cycles. These the other thing that we've been sort of playing with is putting these into silicon bodies. So until now, these have mostly been explored as sort of standalone materials, but they're very sticky. They are pretty fragile, like they're pretty sort of non-resistant to kind of impacts, which means for something at sort of the macro scale or something that interacts with another system, they have fairly limited use. So we've been looking at sort of putting them into open source soft robotic designs that aren't typically used for things like pneumatic actuators, and using the gel instead to actuate these sort of bodies. So they're, as I said, they're pretty slow. I'm going to kind of move through these videos by hand because this one, its total time is about 24 hours. So it takes a really long time, but it will curl up, and in this case, it takes around sort of like 5 hours to deswell. So we know with these we're not at the kind of optimal operating point of these materials, because the materials that we're working with are actually quite widely reported in surrounding literature. Pinapam, which is the material that we work with, is sort of termed like the poster child for this type of material because it's very easy to make, and a lot of people sort of conduct experiments with it. But what we've shown using this material is that we get much better force output by encapsulating it in these silicon bodies, meaning that it's made to sort of be more usable, as in we can get more force out of something that would sort of otherwise fall apart once it reaches a certain tipping point. So we work a little bit with sort of embedding heating elements in the material itself, but the main thing we've been looking at is how we could use this for things that would operate in like natural sort of environments. So something that could be used to open and close a small lamp in order to feed something like the robot, or could be used sort of in sampling in something like a farming environment. So we did some temperature recording and looked at how we got these really sort of nice repeatable daily cycles of temperature around 32 degrees, which is the actuation point of this material that we're making. We're also using 3D printing to fabricate these into kind of more repeatable and sort of just higher quality structures than trying to put them into things that are cast into molds. And we've had some nice results with DLA printing, so with UV curing and slices to create small sort of like hollow actuatable structures that we use for things like sort of micro pumps. These could also maybe be used for sort of morphing robots, the idea of joining robots together. So if you have something that's very slow to actuate, but once it's actuated, it will kind of hold shape with a decent amount of force. This could also be used for sort of this idea of joining things together. Okay, so I'm just going to talk briefly about this other project, which is pretty kind of disconnected from what we're looking at, but I was sort of thinking about the diversity of things that you have here, and thought that might want to bring in some of the elements of the other things that we're working with. This is a project that we're doing with neuroscience at Heidelberg University, where we're exploring the idea of using haptics, so using the idea of artificial touch as a way of
But my friend had a similar idea.
okay.
Just in theory.
In theory, okay. So yeah, well.
And here it is.
And here it goes.
Yeah.
And here it is. So we were sort of working with the idea of using haptic feedback in place of visual feedback to see how that works, how that sort of compares in efficacy to visual feedback. So this sort of neurohaptic feedback is used for treatment of things like ADHD, or used sort of, I guess, therapeutically for things like ADHD, where people are engaging with the type of feedback in order to typically to focus, so to try and improve their focus on a task by learning to sort of regulate their own behaviour in some way. And so for this, the sort of the theory that we're working with is that the visual aspect of this can be quite non-intuitive, it can be very time-consuming, and the studies seem to report a fairly high dropout rate for people engaged in this type of thing. So we've created a really simple system just using very simple kind of tactile actuators, and we've arranged them in a pattern that we think sort of reflects some of the visual games that people use for this type of therapy. And we're currently conducting experiments to compare these two. So participants are involved in a task of sort of proprioceptive task where they're moving counters from one side to another, and that counters will fit through the sort of shape in a box. And then we're looking at how this feedback compares to visual feedback in terms of how the box improves. Okay, so the last thing that I wanted to talk a bit about was how art, technology, environment, and play come into some of these things and into the sort of community in Kyoto that I think reflects best what we see here. So we've been using these types of demonstrators in things like Environment Now, which was an event at the London Science Museum, which was sort of just trying to engage children typically with technology that was targeting environmental problems. Kyoto also has like a really nice kind of art overlap with science, which I think has been really successful in doing things like sort of presenting kind of hidden science. So we had an exhibition recently that showcased a lot of different work on things like microbiology projects, but blown up to sort of huge scale and linked with sound installations to things like Regenbox, which is a really nice project by a friend of mine that looks at. He has a sort of website where he brings old but not open source, but I guess like public domain work around sustainable energy into sort of like trying to bring it back into sort of public awareness. And one of those projects is Regenbox, which is a box for regenerating, for recharging non-alkali batteries that you can build yourself using a kit with sort of very simple components. Yes, yeah, he's from France, based in France. And then our maker spaces seem to have like a really nice running theme of recycling and repurposing for things like sound art. Like sound art seems to be a really sort of recurring theme. This is Material in Kyoto, which is a sort of repurposed old building, and there's a couple of other places, DIY Lab and the Maker Garage, which have sort of different approaches to their sort of layout. But a lot of different groups operate out of these different spaces, and a lot of the focus has been on kind of sound and music and how we can use sound in order to kind of play with people's awareness of the space around them. So these are some sort of ongoing projects that come out of the communities that I personally work with. One of these is to do with repurposing old electrical equipment. So this primarily started with using barcode readers from supermarkets to create sort of electronic music out of scanning black and white and other sort of surfaces.
Does it have sound?
Yeah, it does. Oh, sorry. Which is sorry. Yeah. Oh, so it might be back on the floor.
How does it sound? Can you sing? Is it a or is it more?
It's sort of, but then the pattern changes with whatever. The sound changes with whatever surface it's on. So yeah, this and the second project. So there's also like a really big sort of modular synthesizer community in Kyoto. So this project looked at repurposing textiles and turning them into a fabric synthesizer. So using this as a way to get people to interact with their physical environment in order to create this kind of sound and to find some sort of personality in the spaces that they're touching. So this is installed in a nice old building in Kyoto, but we also did this project with a sort of tree, and the fabric reacts to the electrical capacitance of your body, like a person touching it. But anything.
Regular fabric.
Sorry?
Regular fabric.
No, it's conductive. Yeah. Well, I mean, it's not so special. It's just electrically conductive. Yeah. But we also do this with things like creating sound installations with trees, where you play and synthesize so that you have this kind of random aspect that's created by the tree also kind of playing with you, and the part of it that you can't control. Just as a way to kind of help people to sort of reconnect with their environments a little bit. So, just some brief images that kind of tie all this stuff together. We're sort of continuing to look at how interfacing with the natural elements in the environment can contribute to long-term robot self-sustainability, and how we can benefit from things like multifunctionality of these different materials. We're hoping that these robots, sensors, energy autonomous devices will kind of make their way into IoT devices, and that stuff like these novel sensor and robot designs can maybe help us to really understand our environment, both in kind of like a analytical, sensor-based way, but also just in a kind of, it's a way that's a bit more playful, and yeah, it just helps us find some fun in the things that we do.